Hi guys, how are you? Today is early weekend morning. Kind of tired, but it's my task to make it this lecture. We will someday we will be a smart engineer. When you learn and learn more and more. You know what I mean? So today we will learn about importance of reducing fault current, mechanical strengths. Let's go more. So, we already learned about magnetic force, right? I will say on purpose, we make it this is a good way, is a positive. And without our intention or without our purpose, it made it is our accident, it made it is we say negative. So magnetic forces, a positive example is a motor, right? If you guys, kind of confused what I'm saying now, you guys, which means you guys skip the lecture. Look at that. The motors, the motors are rotating. But how? That's why we previous lecture we learned the magnetic forces direction, right? So look at that. For example, this is DC, right? So this is power supply. So look at that. The current is, this, I will say this part is number one, and this part is number two, okay? Number one is getting the current inside of the screen, right? But look at that. Here's flux is N to S. Flux is this way. So look at that. Flux is this way, but the current is inside, right? Inside. So if I, rotating, you guys should remember the cross products, right? Cross products is rotating, right? The thumb is here, the result. So now this time is magnetic forces direction. And the other side, number two, here, look at that. The current is coming out to me, right? But the flux is the same. So look at that. From here, from current is coming out, right? And to the rotation, to the flux way. The thumb is here, up, right? That's why. So now the motor is rotating, not clockwise, right? Clockwise is this, not clockwise. Yeah. Let's move on more. So all power facilities have to withstand the short circuit current thermally and mechanically. Thermal means like a heat, right? So as you can see, this waveform is a short circuit current waveform. What I mean is fault current is actually include many of bad current, what we don't like for example, a short circuit current. Okay. So yeah, I will say just a fault current or a short circuit current. So okay, this is different, but what I mean is short circuit current is one of the most bigger bad current, fault current. That's why, yeah, that's why I will choose this one. So look at that. Let's move on. I will explain. So I said you have to withstand the thermal mechanically, right? So power facilities, for example, transformer, generation, motor, everything, you say. So thermal means heat, right? So thermal damage is, proportional I to resistance and time. First of all, as you guys we know CB, right? CB is a circuit breaker, right? Look at that. Here's our transformer, and here's like a CB. circuit breaker, and if the fault current happened, CBs operate and prevent the fault current. That's the CB's main point, main purpose, right? But here's the thing: the CB could prevent, the thermal damage. You know what I mean? Because I said it's proportional to the time. So if a CB is run, operate well, if it's cut the current well, we could protect the thermal damage. You know what I mean, from the CB. When the fault current happened, since the CB is operated, and we could protect the thermal damage to the from our power supplies, like power facilities. Got it right? But here, current value is RMS value. So simply thinking, this value is this blue wave, as you can see. But yeah, that's it. This thermal damage part is since we use a circuit breaker, if it operate well, we could protect the thermal damage from the CB, right? And the metal part is, look at that. Okay. Okay. The metal part is here. The metal part is here. Fault current. Fault current mechanically. You know what I mean? So which means, first of all, we need to know multiply 2 and 2 is different. For example, 3 multiplied 2 is 6 and 3 2 9. If the number is more bigger, it will be the numbers differences is the gaps really big. You know what I mean? So look at that. In ICE standard, in high voltages, the values, the fault current is, the values, it gotta be almost 2.6 times high. It could be high. Look at that. As you can see here, this gap. So as I said, the mechanical, look at that. Let's move on. I will show you guys. Yeah. So here, magnetic force is actually real force or something, it's moving something, right? So look at that. That's why it get the course, it got the breakdown. So what I meant is important thing is it did something break the batteries. You know what I mean? It break actually. Oh, look at that. So what I mean is here, as you guys can see, the current is to 2. So which means so this value is not RMS. We say instantaneous values. So which means the current value, peak to peak point, it has to withstand this value. You know what I mean? I will explain why when the fault current it happened, why the current waveform is asymmetric, like the red. To learn about this, I will make the lectures about it when we start circuits. But to understand this, I will just explain a little bit. To understand this, we have to learn about the Lenz's law and what is that inductor. Like that, if we accumulate our little bit of knowledges, we could understand it. We don't need to struggle to memorize it. We will just understand it, why it happened. Okay. So, sorry, I'm kind of digress from the main point. So the peak values, as I said, peak values, it could, increase 2.6 times. Like, so it has to, it has to, you know, power pressure, it has to withstand these damages, okay? But as you know, CB cannot prevent this mechanical damages. CBs only could, prevent the thermal damage, okay? If we CBs, the circuit breakers, prevent the thermally and mechanically, we always use CBs, more higher CBs, but it doesn't, okay? We need to remember this. So that's why, many engineers always try to think to reduce the fault current values. That's why we need it. If we, if the CBs could prevent everything, we don't need to, right? So if we know about this concept and knowledge, we could suggest some idea and we will, try to find out the solution. Let's go over. Let's move on. So look at that. Reducing fault current solutions. I will say just as tools. There's many, many things. Increase the impedance of electric facilities. Impedance means resistor, right? But if we, we could, adjust the impedance of the facilities. But there's a pros and cons. I'll explain later about it. And we could also install current limiting reactor to, to reduce the fault current values. Like, try to understand this concept, guys. Okay? Today lecture is done. Thank you.